Welcome to our next video for Stat 420. In this video, we're going to talk about how do we identify unusual observations. We're going to talk about leverage. We're going to talk about high residuals and how we kind of put those two ideas together to talk about data points with high influence that we should consider for removal because of how much they can influence the model estimates that we use here. So we're considering removing data. I also want to kind of situate this in a larger picture here. We're not doing a lot of data cleaning in this course. Maybe we'll do a little bit more when we get to the end if we have some time. But just kind of keeping our mind open here. Why should we ever consider removing data? When do we have that conversation? And so some obvious things would be, number one, we believe we have a recording mistake with one of our data points, that it just doesn't make sense, or we just happen to know that it's a recording mistake. That would be fine to remove. And then what we're going to kind of get into this video is kind of this anomalous readings one, where maybe the data is just highly unusual, maybe the residual is really large, and kind of tacking on to that, it's going to have a large influence on the model we fit, and we don't want kind of this 1 or 2 or 3 high influence values to kind of pull the whole model towards them. And rather, we want a model that kind of represents what most of our data is doing, rather than what a couple of these really extreme values are kind of doing and pulling the model towards. And then kind of going along with recording mistakes would just be non-serious answers. So whenever I usually do a lot of like student surveys for data, when I teach, especially like the lower level courses, because students really like those. And there's always students who just kind of put silly answers because they want to. So they're not really recording mistakes, but they're also not, they're just not serious. So I take them out. If you say that you're going to make, $50 million in 5 years from now, then I don't believe you, and I'm going to take your data point out because it makes the variable no fun to analyze with $50 million hanging around all the serious answers. So yeah, that would just be, I guess, be another reason why we might consider removing data before analysis. So when do we care? Well, contextually, if we know that it's flawed or imprecise, it makes sense to drop it because it's just bad data. And statistically, as I mentioned, we care because it might have a high influence and it's going to affect the whole model. It's going to affect my coefficients, and I don't, again, want those 1 or 2 values, or that small handful of values, to highly influence the model away from what most of the data in that trend seems to be. So what does influence look like? And so there's 2 ideas that are paired up in this term influence as we're using it statistically here. The first would be that we have a high residual. So a high residual is when we have a large distance from the best fit line, that there is a lot of error in a particular data point. There's also this idea of high leverage, and that's usually going to be represented by data points that are kind of far off to one edge of the predictor spectrum. So if I have a data point that is really far away, you kind of think about how much this line can change. And I can fit all this data pretty well with different lines that look like this, or this, or this, right? And this point is actually going to have a lot of leverage here on how this model gets fit. So then if I put these 2 ideas together, I'm really concerned whenever I have data points that have a high residual and a lot of leverage based on their position, based on having kind of predictor values that are kind of along the edge of the spectrum of what I've observed, because those data points are really going to have a lot of influence on that model. Whether or not I include them becomes a really important choice. So let's talk a little bit about leverage first. Leverage mathematically is a little bit confusing, especially if we're talking in the context of multiple regression. But essentially what's going on is we want to measure the leverage of a particular observation based on its predictor values. So in the case of simple linear regression, it's a little bit easier to think about, which is why I kind of stuck this over here, is we're looking at this. So for a particular data point, we have our one predictor variable, And we're looking at the predictor value in relation to the mean of x, where the larger this value is, the larger the leverage is. And there's some other terms in here as well, like honestly, these terms are constant for all observations. So 1 over n is just 1 over the number of observations. So that is always in every leverage calculation for every data point. And then this sum of squares of x is also going to be a constant here. So this is really the only part that's going to vary from observation to observation. The rest of this is just kind of standardizing the value to some scale. So bottom line, the larger a predictor value is from the mean of that predictor, the larger the leverage is. Now, in the context of multiple regression, though, I have multiple predictor variables, and I would use matrix multiplication to make this same calculation, which quite honestly is not very easy to follow unless you're very fluent with linear algebra. And quite honestly, I'm not either. I just kind of, at this point, take it for granted that I went through grad school and at one point sort of understood this, and now I just use it and I'm okay looking at this and saying this is true. But essentially what we're doing is there's this thing called the hat matrix. The hat matrix comes from this idea because it is the thing that I multiply y by to turn y into y hat. And it's going to be based on this derivation up here because, as we very briefly talked about and did a little bit of hand waving before, y hat equals our x matrix, all of our predictor values times this beta hat matrix, which represents kind of our column of best estimates of beta hat naught, beta hat 1, beta hat 2, beta hat 3, all that stuff that you probably don't care about anymore. And we can represent this with this expression right here that can be an expression of y. And the hat matrix is this piece right here that we kind of pull out. And again, it's this thing that we multiply by y to get y hat. The leverage of a particular observation is going to be found by taking the diagonal of the hat matrix. So the leverage of the ith data point is going to be the ith diagonal entry of this hat matrix. We're not going to talk about why that's true. We're not going to break it down any more than this, other than I just want to give you a little bit of context. There's this thing called the hat matrix. This is why we call it the hat matrix. And for some reason, we can extract the leverage of a data point using that matrix. And it represents this idea. So think conceptually, this idea is what we're going on. There's some complicated math of how we do this in multiple regression. And yay, it works. Okay. Now, how do we decide if a particular observation might have high leverage? So if you think about an observation, we're thinking about like a row in our data where we have kind of a response value, all the predictor values. This is some observation that we've seen. How do we identify these observations that have high leverage? So one benchmark, this is not some kind of set in stone objective thing, it's just a benchmark that you commonly see, is that high leverage is going to be defined as leverage that is more than 2 times the average. So if we take kind of the average leverage values, so if we're thinking in multiple regression, if we take the sum of the diagonal elements and divide by the total number that we took, we get h bar, this average leverage, and then we multiply that by 2, and that becomes kind of this benchmark, that if we have any individual leverages that are beyond this value, that's some pretty high leverage. That's fairly unusually high. So there is this handy function in R called hat values that literally calculates and will produce the hat value for every observation in your data if you plug in this model that we fit. And then you can just see which of these hat values are greater than 2 times the mean of the hat values. So that's pretty handy. Now, so that's the leverage side. What about the outlier side? So this is something that I think makes a lot of sense. Residuals are pretty easy to calculate. We're looking for data values, we're looking for observations that have a relatively high residual. Now, since residuals are going to be scaled in the units of the response variable, that gets a little bit messy because every data context has a different response variable with a different set of units. So for that reason, there's this thing called standardized residuals. And so what we do is we convert residuals to a scale, and we make them normally distributed with mean 0 and variance 1 instead of normally distributed with mean 0 and variance. Um, so there's this calculation that we do. We basically take our residuals, divide by the standard deviation, or sorry, standard error of the residuals times this square root of 1 minus the leverage. And we actually turn these into standardized residuals that follow this standard normal distribution. Again, the only reason we do that is just because we have the standardized scale that we could use in any data context and not have to worry about the scale or the units of the response variable being different all the time. So we have that. We can identify when standardized residuals are unusual. Again, oftentimes, if they're above 2 times the average standardized residual, that's a little bit unusual. And we take these two ideas of leverage and standardized residuals and put them together. So we want to know when data points have a high leverage and a high standardized residual, and we kind of give them this score, if you will, depending on how high those two things are. And there's this expression, or I guess I should call it an equation since there's an equal sign, called Cook's distance, which puts those two ideas together and is one way to measure influence. So this is the equation for Cook's distance. I don't really care, or we don't really care that much about why the formula is exactly why it is the way it is. Again, there's other ways that we can measure influence. It doesn't have to be Cook's distance, but this is kind of the standard in statistics to measure influence. But the important part is it is a function of the standardized residuals as well as the leverage of each observation. And this is a function that you should definitely know. Cook's distance of a model produces the Cook value, or the Cook distance, for every observation in our data. Again, we're interested in unusually high influence. We want to know which values are unusually high in influence, because that means that they have a lot of leverage and they have a high residual, and they're going to have a lot of, therefore, influence on the model that we fit. So Cook's distance that's unusual is usually going to be denoted as being more than 4 over n, where n is going to, again, be the number of observations that we have in this data. So if it's kind of 4 over n, the Cook's distance is fairly high, and it's going to have a lot of influence. One thing I want to mention before I go any farther, because I don't think I answered this, you might be wondering here, well, wait a second. What about residuals like this one? Like, why is this not going to have a lot of influence on the model? And that's a good question that I wanted to make sure that I addressed. And it's, again, going to come down to its position. So I can have a residual right here, but if it's kind of in the middle of my X range, notice here that whether this data point is here or here or here, it's only going to shift the line kind of collectively a little bit up, but not all that much, and it's still going to fit the data pretty well. So it's not just having a high residual that makes influence happen. It has to also do with its position with respect to the x-axis, because the orange line represents how this line moves, and we can see really only in this case for both ideas to come together, both leverage and high residual, where we see that kind of significant shift in that model, in that line. Okay, so with that said, that's why we care about both these ideas together being present. Now, for evaluating Cook's distance, again, we can just take the Cook's distance of a model, and this is just going to be the list of the Cook's distance for every observation that we have. And then we can just do a logical statement of greater than 4 divided by the length of the Cook's distance model, or the number of observations in the data that we're working with. This is probably a little bit more reliable because there might be some missing data, there might be some empty observations, so this ensures that we're not dividing by more than we should be for that reason. And this is going to produce a logical list, meaning that, or a logical vector, meaning that we're going to have a list of true and falses. So true if this is the case, false if this is not true. So if we set the criteria to something like 4 over the length, we're going to get mostly all falses, if not all falses, and maybe 1 or 2 or a handful of trues, meaning there's going to be a couple observations with the Cook's distance that are pretty high influence. Which brings to the question, okay, well, what do we do with that? So we can find when this is the case, we can identify values, we can identify observations where this is the case. What do we do about it? Well, one option is to consider dropping them from the model and seeing how much the model changes by removing those values. Now, we can change this criteria. We can kind of play around with this as we need. So if we want to be a little bit more choosy, or maybe I should say, we want to be a little bit more like raise the bar pretty high before we remove a value. Well, we can just make this benchmark a little bit higher. We can make it 5 or something like that, and we can see how much the model changes. Or if we're okay just kind of letting some values go, we can keep it low. We can keep it around 4 or maybe even a little bit lower if we wish. If we are okay just dropping these more high influence values, but really it's going to be context that dictates what we should be doing and how stingy we should be about letting data values go from our model. But it certainly makes sense to at least fit a model without some of these high influence points just to see how much the model changes when we do. So one way that we can do that is to identify the values that we want to keep. So let's say we want to keep values that have less than or equal to this benchmark for their Cook's distance. And then we can use the subset argument in the LM function to only fit a model with this list. Or I keep saying list, I guess it's a vector. And this vector is going to be a logical vector of trues and falses. So basically it's going to be true when this is met. It's going to be false when this is not met. And so we set it up this way on purpose because we want to hold on to the ones that don't have a high influence here. We want to hold on to the ones that are below the benchmark. So this is going to output to be true in that case. And we want to subset to include the true observations. We want to include the ones that fit this criteria. Another way that you could do this, by the way, is that you could also just kind of subset your data. You could do like a which statement. So if your data is called df, you could do df bracket which this is the case. And then you could just run a linear model where data equals that subset that you just created. That would also be fine. Though this is probably a little bit simpler. It also keeps you from having to create copies of your data, which can get a little bit messy and complicated. So this is probably the preferred way for one, if not 2 reasons there. But yeah, that's how we can kind of get rid of those, fit the model again, see how much they change. But ultimately, this question of removing or not removing is really contextual. So it shouldn't just come down to, oh, well, the Cook's distance is above 4 over n, it should be removed. It's really not that simple. It really just depends contextually on what's going on. And that's not something that this class can do a whole lot to help you with because we're not covering a specific discipline. You're going to encounter data in a lot of different situations. So I guess all I can say is give this plug for don't just remove values because a Cook's distance is high. Remove them because you're comparing what the model could look like. You're actually looking at what the observation is and deciding, is this a problem? Is this a mistake? Is this a contextually different unit? Is there something about this unit that makes it different from the rest of the data that I collected? And deciding what to do about that. So I think in the book there's an example with cars where they're working on this. And so cars obviously can be very different. So maybe you're going to identify that there is a category of cars that has typically high residuals and maybe even high influence. And maybe that decides how you kind of approach your model, whether you need to add another predictor variable to represent some of those unusual categories that you've identified, right? So this is really promoting more thinking about your model not just simple, oh, remove it and be done with it. So, um, so yeah. One other thing that I'll mention here is that if you have that if you're removing data values, these are not fixing assumption violations. So I know we talked about this kind of in the same chapter, but removing values that have a high residual and high leverage isn't going to make your non-normally distributed residuals all of a sudden normally distributed, because we're only removing a couple data points most likely, and these assumption violations are usually more systematic issues. Um, so for that reason, just kind of keep that in mind, that if you have assumption violations, we'll talk more about that when we get to transformations in the next chapter and what we can do, especially when we have non-constant variance.